Okay, welcome to the second video in radioactivity. We're going to be looking at today the three types of radiation which you will have met throughout school, i.e. alpha, beta and gamma. We're going to be talking about how we can detect and distinguish them, and a little bit of revision from year 12 in terms of changes in the nucleus and what we call the decay equations. Again, a little bit of history just to start us off and to set the scene. Three types of radiation that can be separated by electric or magnetic fields. This is important in your understanding of how originally early scientists worked out their properties, and their behaviour in magnetic and electric fields is quite important. The whole concept of ionisation, which you should know from earlier studies, which is the process of adding or removing electrons. Normally, in our case, it's going to be the removal we talk about when things are ionised using radioactive sources. The concept of ionisation is really how radioactivity is detected. Without it, we would not really be able to detect radiation, and the more strongly ionising the radiation is, the more rapidly it dissipates its energy when it passes through materials. So this idea that alpha and beta are more ionising than gamma, we will look at when we consider the properties of them. And really, just to remember the important fact that how radioactive something is nothing to do with physical conditions such as heat, etc. It just depends on the type of nuclei that are present and how many of them there are. Okay, so very simple diagram, important to understand. You might remember Fleming's left-hand rule. Fleming's left-hand rule gives you an idea of when a current is travelling in a magnetic field, there's a force on it, and you can work out the direction by holding your left hand out and separating your three fingers your two fingers and your thumb at right angles. So if you're using this diagram, you can see that the magnetic field is into the page, the B field is into the page, and we can see that the alpha particles in this situation would travel upwards. Now, if you use your left hand and point your first finger into the page, your second finger is the current going across the screen from left to right, and you'll see that your thumb points upwards. Remember, using Fleming's left-hand rule, the direction of the current is assumed to be the way that a positive ion would travel. So it's conventional current, if you like, where we don't look at electron flow, we're looking at the way that positive charges would move. So this diagram shows that the alpha particle bends slightly, the gamma radiation does not bend, and the beta, which I've shown here with an E negative, because we know now it's an electron, the beta particle bends considerably more the other way around. So what does it tell us? Well, it definitely tells us from this that the alpha must be bigger. They bend less, so therefore they're bigger, and also that they're positive. The beta, it tells us that they're negative, and because they bend more, they must be smaller, so the force has a greater effect. And the gamma radiation is not charged, it is just high energy photons consisting of as part of the electromagnetic spectrum, which you've met throughout school. So how do we detect radiation? As mentioned, this is all about ionisation, so it's their effect on matter. They're all detected by this. Because alpha and beta are charged, they're highly ionising as they collide with other atoms. They're also larger. Alpha obviously much bigger. Alpha are the biggest, beta are the second biggest, and they're both charged. So there is far more chance of them knocking out electrons and interacting in that fashion. Gamma can ionise, it is capable of ejecting electrons. Your studies from year 12 in terms of photon absorption, etc. might help you with that. But it's less so. It's far more penetrative, which we'll look at in a second, but it's less ionising. How do we detect them? The two ways that you definitely will have met in the lab at school. The first one, some kind of ionisation chamber, which is kind of like a GM tube, which we'll look at in a second. This is quite simply where here we've got our radioactive source, we've got our radiation, whether it be alpha or beta or gamma coming through, and during the process here between these two plates, it's knocking off electrons, so you end up with positive and negatively charged ions, and it positively charged ions and negatively charged electrons. These separate, are attracted to the appropriate plates, and this causes a current to flow around the circuit. So the more radiation that's ionising, the more current you get flowing around the circuit. There's also a cloud chamber, which is sometimes mentioned. You don't need to know it for the spec, but this is when you've got an alcohol vapour that condenses as the particles travel through. So you see the tracks, and there's loads of pictures you can see online looking at what these types of radiation look like and the paths that they leave. The GM tube, probably worth spending a little bit of time looking at, because you will have used one in the lab. It contains air or argon, sometimes at a low pressure. The reason being here is that gases conduct electricity much better at lower pressure, as the ions travel further between collisions, so they can get across the gap, if you like. A GM tube registers the arrival of individual particles, and you can see how it's connected. It's connected in a circuit. We've just got a potential difference, we've got a resistor, and this counter is kind of acting as a voltmeter, but it's picking up a pulse of current. So as particles are ionised in there, ions are accelerated by a field to plates, and this causes an avalanche of charge, a little pulse of current or a change in voltage that's picked up by the counter. There is a problem with this. They've only got a certain sort of resolution, if you like. They suffer from something called dead time, and this is that if there's too much radiation coming through while a pulse is being generated from one ionisation event, they can miss the next one. It can happen at the same time, and GM tubes suffer from this thing called dead time, which is normally about 200 microseconds, which means they've got a maximum count rate of about 5,000 per second. So in summary, we've got some basic properties which you need to know. We've talked about some of them here in this short video. What are alpha particles? We know this: 2 protons, 2 neutrons, a helium nucleus. What's a beta particle? It can either be an electron or a positron, depending whether it's B negative or B plus. Gamma radiation is photons, electromagnetic spectrums. They're in the mega electron volts energy band. Mass approximately 4U. Beta not very much, about 0.00055 U. Gamma ray, obviously the photons, no mass. Charge, it's got +2. So +2 means 2 times 1.6 times 10 to the minus 19, and it's also constant for a given source. The energy is constant for a given source, obviously the charges. Beta particles, they've got a charge of -1, so 1.6 times 10 to the minus 19, and they vary to a maximum. And if you think back, this is because from year 12 revision, when a beta particle comes out, it also comes out with a neutrino or an antineutrino, and that shares some of the energy that comes out with each decay. Gamma radiation, there's no charge, and again, that's constants for a given source. How ionising are they? Alpha particles, about 10 to the 4 ions per millimetre. Beta particle, about 100 ions per millimetre, and gamma radiation, very weak. You wouldn't really measure it across the millimetre range. Speed, we've got approximately 5% of the speed of light, so still impressive, not as impressive as beta, up to 90% of the speed of light, and gamma rays obviously at the speed of light. Penetration of alpha particles, not very good. They're stopped by paper, skin, or just a few centimetres in air. Beta particles, they're stopped by 3 millimetres of aluminium, or about 1 metre of air. Gamma radiation, it's the inverse square law, which we are coming to. It's reduced significantly by several centimetres of lead. And these properties again give you a hint as to the physical properties of the individual radiation. Obviously alpha's larger particles, so they're not very good at getting through things. Are they affected by electrical magnetic fields? Yes, they are. Both beta particles, yes, they are, and they're in the opposite direction to alpha, and more so because they are lighter. The gamma radiation, they're not affected by either electrical or magnetic because there's no charge. Okay, just a bit of a reminder from year 12. We need to know this nuclear notation. We're going to quickly look at some alpha, beta and gamma equations. So X, in our case here, X is the nuclide, and it contains Z protons, and A is the mass number. So if you wanted the number of protons, you'd do A minus, if you wanted the number of neutrons, you'd do A minus Z. Okay, so let's just have a quick look through. This is an alpha. This is what we would have as an alpha decay equation. So whatever A is, the mass number reduces by 4, the proton number reduces by 2. This is the alpha particle, and you're left with a daughter nucleus after the alpha emission, and this is A-4, Z-2 for the numbers. We'll do some examples in a second. A beta, in this case it's the beta negative, which is the electron, so no change to the mass number, but in this transformation a neutron turns into a proton, so Z goes up by 1, and we've also got our antineutrino here for conservation laws. This would be our beta positive emission. Okay, you've got this time it's Z-1 because a proton turns into a neutron, but no change to the mass number. And then finally a gamma emission. There is no equation because there's no change at all. This is just where an excited nucleus effectively calms down or relaxes by releasing gamma radiation, and very often the gamma radiation comes part of an alpha or a beta emission. Okay, and then just to finish, some very quick equations to give you an idea of some very simple questions you could get asked. So alpha emissions, here we've got uranium-238. It decays to thorium. So our full equation would be 92 drops to 90. Remember, in exams you'd never be expected to know proton numbers and mass numbers. You'd always be given them. So 238 goes to 234, 92 goes to 90 because we've lost 2 protons and neutrons. And this leaves us with thorium, and there's our alpha particle. And if it decayed again, we'd have thorium 90, protons going down to radon 88. So 2 and then 4 off the mass number. So it's fairly straightforward. The beta emissions, so we've got 64 mass number, 29 of the proton number. And if you remember, with the beta emission, we've got a neutron turn into a proton. So 29 goes to 30, 64 stays the same. Here's our beta negative or electron and the antineutrino. And then, okay, and this is, we've got 15. We've got 15 protons, and this goes to 16, so 15 goes up to 16, where we've got a neutron turn into a proton. The mass number stays the same, and then we're showing here the beta negative particle as well as the antineutrino. And then finally, just a different style of question, we've got bismuth-213 decays by beta negative to form polonium, then decays by alpha to form lead, that decays by beta negative to form stable bismuth again, so it goes back to bismuth. What are the 3 product nuclides? So if bismuth decays by beta negative, then we must have here that the 83 protons turns to 84 into polonium, but the mass number stays the same, so that's the first nuclide. And then polon decays by alpha to form lead. Polonium, decays by alpha to form lead, so 84 will go to 82, 213 drops by 4 to 209, so there's our lead. And then if this decays by beta negative again, 82 is going to go to 83 because it's a beta negative, a neutron's turned into a proton, and 209 stays the same, so we're back to a different isotope of bismuth.